Alright, welcome to this recording about science. So we're going to talk about science on its most fundamental level. It is a method to learn. It's how we learn about our world. And what I want to address immediately is this idea that science is not for creative types. And that is absolutely not true. The best scientists are the most creative. They're the most imaginative. As Einstein said, the true sign of intelligence is not knowledge, but imagination. Because it's going to be with imagination that you're going to make new connections to understand the world. So let's remember that. Now, the scientific method, it's not any one method, but it is a consistent and logical manner of framing questions about the world. Right? How do you systematically find answers to those questions? And the key to it is that it is based on empirical evidence, demonstrated evidence. And as we move through an example of this, I hope to make that distinction between evidence that is conjured versus demonstrated evidence more apparent. Now, a more formal definition could include the observation, identification, description, experimental investigation, and theoretical explanation of phenomena. And that's quite a mouthful. So again, I want you to not think about the scientific method as a very specific stepwise protocol, but rather a general set of practices that we move through to gain information based on evidence to our world. All right. Now, if we look through the next couple slides, we're going to kind of map these out. So common research practices. If you want to research something, if you want to learn more about something, then we're going to start with observation. And some people will call this very first step its own kind of science. They call it discovery science or descriptive science. When the goal here is simply to observe something and record those observations. Now, it's incredibly difficult to record and observe something without starting to ask questions about it. And so then we're going to take our observation and we're going to frame questions about it. And from those questions, we're going to propose a hypothesis. And we're going to see that hypotheses are kind of the key to data-driven science. Right? It's a testable explanation of the observation. And that testability is really going to be the true mark of a good hypothesis versus a bad hypothesis. Right? So from the hypothesis, you're going to make a prediction about some condition that should exist if the hypothesis is not wrong. Right? And as we go through an example, I think this will become more clear. So you're going to form a hypothesis, make a prediction, and then test it. Run the experiment. And we'll see that this kind of step 4 and 5 really involve a tremendous amount of imagination, a tremendous amount of creativity, and can be very challenging, but also a lot of fun. So after we test our prediction, we gather data, right? We build a model, and then we look at the results of that test. We see that data, and we say, does it support our prediction, or does it invalidate our prediction? And both are of value, right? So then we can come to conclusions, and hence learn more about the situation, the phenomenon that we are investigating. Now, let's use a very simple example. I want to show you that you do this every day. That everyone is a scientist. And we talked about that when we talked about brain rules in our very first day of class. You are hardwired to discover about your world. All right? So let's say you get in your car and you turn the key and nothing happens. What is the first thing that comes to your mind? Say it out loud now. Right? I imagine many of you said, oh, battery's dead. Right? Boom! Hypothesis right there. You've hypothesized that your car won't start because the battery is dead. Okay? So you test it. You turn the key again. Still doesn't start. All right? So now what do? Get out of your car. Say, hey, can someone jump me? Or you put a new battery in. So again, you're now running an experiment to see if in fact your hypothesis is true. If when you put a new battery in that you verified has charge and the car starts, that validates or supports your hypothesis that the first battery was dead. Let's say you put a new battery in there and the car still doesn't start. What's another hypothesis? Well, maybe it's the starter. But to be honest with you, I'm not a mechanic. I don't know how many of you are, but I don't have many more hypotheses beyond that because I don't understand cars. Now, if I take it to my mechanic, all of a sudden she can look at that and immediately starts to generates a huge list of hypotheses of everything that she can test to try to figure out why the car won't start. So that is one reason why we take courses like this, why we need to build a library of information in our head so that we can make reasonable hypotheses. If I don't know anything about a car, I can't even begin to guess. I have to learn more. So we have to accumulate a group of facts that then we can play with. But it's the imagination that we have to bring into play here to see how those facts fit together and how they can be applied to the current situation. Again, in this case, that my car won't start. Now, let's go back to empirical evidence. So if I take the battery out and put a new one in, the car starts. That's evidence that the battery was the problem because I've replaced it and now my car starts. But what if, alternatively, I say my hypothesis is not a good one. It's not testable because I say it's the magical, invisible, undetectable car fairies that are unhappy. That is why my car does not start. What can I do with that? I can't do anything with that. Right? So I take my car to my mechanic, and my mechanic does a bunch of stuff in there, and I don't know what it is, and then all of a sudden my car starts. And she says, oh, you needed a new starter or, distributor cap or whatever. And I say, that is fine. You have gone through the ritual to make the car fairies happy again. And now my car starts. Can you prove or disprove that you are wrong with that hypothesis? You can't, because the car fairies are undetectable. At the same time, it's not a very good hypothesis because I can't test it, right? There's no empirical evidence. Right? Does that make sense? So I want you to think about that. It's a ludicrous example. It's extreme. But think about that. The ability to test something is really the kind of the real value in a hypothesis. All right? Now, again, we did that, and we do that kind of stuff every day. Remember, we are all scientists, and that is our fifth brain rule. I want you to remember those. We're programmed to discover things. Now, let's delve into the experimental method just a little bit more and introduce the idea of controls. So controls are going to help us discern which variables are having an impact on our phenomenon. Okay? And so we have an example here through a series of pictures about growing plants. So I got this from a major's textbook, and what you see here is two plants sitting on a windowsill. And your friend has the same plant as you do, and they added fertilizer to their plant, but you did not. And lo and behold, their plant flowers. So you form a hypothesis, and the hypothesis says that plants require fertilizer to produce flowers. So you run an experiment. You take repeats. You take 6 plants for your experimental treatment, and you add fertilizer. But then you have a control treatment, where you have the same same kind of plant, 6 of them in a different window, and you don't add fertilizer. Now, you hypothesize that the plants that are treated with fertilizer will flower, and those that have no fertilizer will not. In reality, though, you have 2 outcomes, theoretically, 2 simplistic outcomes. One is that none of the plants flower, right? That your hypothesis is not supported by the data, that it is incorrect. Alternatively, your data could result in the fact that all the plants that you added fertilizer to flower. This supports your hypothesis that these plants need fertilizer to flower. Now, these are 2 potential data sets from that experiment. Now, if you look at this particular slide, this picture from a book, it says under the conclusion of the experiment in which it flowered, the application of fertilizer induces flowering in this type of plant, confirming your original hypothesis. Now, this is the quote that I have a problem with. It says, pat yourself on the back and apply to graduate school in plant biology. And that is the reason I will never use this book in any of my classes. Right? This is an example of congratulating yourself, putting emotional content into being right, into forming a hypothesis that was supported by your data. That is not good science. A good hypothesis is testable. We have learned information regardless of the data. So the data that come out that say, oh, look, if this had happened where none of the experimental plants had flowers, we've learned something. We've learned that in this situation, adding fertilizer does not induce flowering. There must be something else. And that question that says there must be something else is what science is all about. Now, use your imagination. What other variables might be involved? Is it the amount of light that's coming in through the window? Is it the temperature? All of these things you have to think about, and this is why you need that control, right? That control experiment, or that control group, validates the variable in the case of fertilizers causing flowering, that the fertilizer was the variable that caused flowering. What if the control group had flowered as well? Now all of a sudden you know it's not necessarily the fertilizer. There may be some other variable, but you wouldn't have known that had you not run the controls. This is something that takes a little bit of practice, and we will work on throughout the quarter, and is super important when you apply the scientific method. All right. So this goes back to the idea, and this is another famous scientist. If you've not read anything by Richard Feynman, you should. It doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with the experiment, it's wrong. And I will tell you that I have seen numerous, well-respected, incredibly intelligent scientists who would not let go of their pet hypothesis. They put personal, emotional content into it, and it's bad science. All right? Now, let's explore this idea of controls a little bit more in one more example. So in this example, we're going to talk about olestra. So olestra may be something that you're familiar with or not. But basically, it was a fat substitute. So we, as people, have a system in place that rewards us for certain actions. And this is set up from evolution. So when I eat potato chips, in general, they taste pretty good because they're soaked in fat and oil. And evolutionarily, our species evolved in an environment where calories weren't free. That the more calories you got into you, the more likely you were to survive, because there were many, many periods of time where no calories were available. So when we eat things that are high in calorie content, like fat, it tastes good, and that encourages us to eat more. That becomes a problem in modern society where we have an abundance of calories available to us, not necessarily nutritious. So olestra was an opportunity to make a fat substitute that was not absorbed by the body, that would register in your mouth as being tasty, but then wasn't absorbed by your intestines and would pass through. So you didn't acquire the calories associated with the taste. Well, a rumor started that said, oh, when I eat these, if this quote-unquote fat substitute is passing through me, it causes cramps. I'm getting cramps from when I eat olestra chips. So that may be anecdotal, story-wise, but what we really want to do is run an experiment. And there's no way to run this experiment well without a control group. So what we do is we form a hypothesis. The hypothesis is that olestra causes intestinal cramps. Let's test it. So we predict then if people who eat potato chips made with olestra will be more likely to get intestinal cramps than those who eat potato chips without olestra. So we have a control group who eats regular potato chips, and we have an experimental group that eats olestra potato chips. And what we find is that 93 out of 529 people get cramps who ate regular potato chips, and 89 out of 563 people who ate olestra chips got cramps as well. So when we look at these results, it does not support our hypothesis, because these numbers are about the same. Okay? So if we break that down, what we want to also consider is that those numbers are really important. How do we generate them? Okay? So when we look here, we have our control group, which involves 529 people. And our olestra group is 563 people. So what you want to remember is that the percentages I generate from this are based on a sizable group. If I had run this experiment with my brother and my Uncle Charlie, where I gave my brother regular potato chips and my Uncle Charlie olestra potato chips, and my Uncle Charlie says, nah, feel great, doesn't cause any cramping at all. And my brother says, oh yeah, I got horrible cramping. What do I do with those results? And so what this again brings into the idea is that repeats are important, that every result, if it's true, should be reproducible. And we see that when we run larger and larger experimental sets. We need lots and lots of numbers to say, is this real? Can I control every variable? And the only way to do that is run enough that you can believe that results. And this is where statistics come into play. And so if you have to take a math, take statistics, because that is where you can look at the math behind this and really understand what number, the numbers of experimental groups that you need to really believe those numbers. So to continue with that idea of statistical significance, you can look at this chart, this infographic on sample size. And this idea again shows you, this is looking at caffeine and saying that there's a trend in caffeine for memory, that the more caffeine you take, the better your memory will be. And this isn't necessarily true anymore as more data has come out, but we're using it as an example just to see that when I use a small data set of only 8 participants, I have a trend that's maybe there, maybe not real. But when I use a data set from dozens and dozens of participants, I definitely see a real effect. All right? Now, causation and correlation are two things that we'll talk a little bit about more later. But the point of this is that when someone says, oh, caffeine doesn't have an effect based on our experiment, well, if you only ran an experiment of 8 people, what you're saying is true, but is it statistically significant? You can manipulate all kinds of numbers. You can manipulate all kinds of outputs. You need to understand these processes well enough that you can stand up and say, hey, you're saying that this is true, but let's look at how you did this experiment. I don't think that's reasonable. So there are 3 kinds of lies: lies, damned lies, and statistics. You can make these numbers say lots of different things, and you need to be aware of that as you think about political polls and when people try to sell you something and they say, oh, this has been proven through clinical studies or what have you. All right? So be aware. So just as a final example of that, the Framingham Heart Study is one that people should be aware of. So this was started in 1948 in Framingham, Massachusetts. And it's an epidemiological study. So it's a study of people and recording kind of how disease spreads among them. So looking at risk factors and what have you. And so this single study, though large and over many decades, is pretty much the sole source of all the recommendations that we have for heart health. Now, it may be a fine experiment, but what we need to do is consider the source population. So I don't have the demographics of Framingham, Massachusetts in 1948, but I'm pretty willing to guess with some degree of confidence that it is not necessarily representative of every group in the nation. So how white was it? How old were those people? Right? All those things have to come into play, and your data is only as good as your experimental group, right? So statistics are only as good as their source data. And that's the last thing I want you to really remember when we start to talk about accumulating numbers and getting results from those numbers.